Okay, so let's go ahead and finish off the quantum mechanics chapter. Where we left off, we were talking about line spectrum and how each atom has its own individual line spectrum, that there's sort of like a footprint. So we talked about why these occur. So we said that if we excite an electron up to a higher energy, then when that same electron relaxes, it will give energy back off. And generally this is in the form of light. Okay, and we said if we were to run that light through a prism, it would split into its own unique fingerprint. And we said that for every atom, every element, has its own fingerprint. Okay, so for instance, the one of hydrogen you can see here, helium, barium. And notice that they're all quite different. Okay, so what we want to do now is use that same idea that we've been building and talk about how that helps explain the actual structure of the atom to us. Okay, so if we talk about the Rutherford model that we talked about before, okay, we said that the electrons of an atom orbit around a dense, positively charged center of mass called the nucleus. Okay, so we have a nucleus in the middle, electrons orbiting around it. But there's a couple problems with this model. So the first problem is that classical physics doesn't work, meaning electrons are small, negatively charged particles spinning around a closely dense, positively charged center. Well, wouldn't the positive and negative charges attract to each other when they eventually collapse? So shouldn't the attraction slow down the electrons, resulting in the electrons collapsing into the nucleus and imploding the atom? Essentially, you would have atom collapse. Okay, so that's one issue. Okay, so electrons are moving charged particles, and theoretically they should give off energy and cause atoms to glow. Okay, there's no experimental evidence of atoms having a glow to them. Okay, so another problem, line spectrum versus continuous spectrum. If the electron were excited according to the Rutherford model, a continuous spectrum would be emitted. Okay, but we have experimental evidence that shows just the opposite. We don't see a continuous spectrum, we see a line spectrum. Okay, so we have lines that are emitted in discrete packets. Okay, so discrete lines at specific wavelengths. And we see that every element has its own emission spectrum. Okay, so those are just a couple problems with the Rutherford model. Well, if that's not exactly true, then what is, what's more close to the truth? What's closer to the truth? Well, if we talk about the Bohr model, Bohr proposed that classical physics view of matter cannot adequately explain the behavior of the electron in the atom. Okay, so we came up with a new theory, which is basically used to explain the microscopic behaviors and characteristics of small pieces of matter and the relationship between the atoms, electrons, and its nucleus, as that was observed experimentally. Okay, so in the Bohr model, he assumed that electrons can exist only in certain discrete orbits that are stationary. Okay, so stationary states or energy levels. More commonly, we call these energy levels. So these electrons are restricted to quantized energy states or energy levels around the nucleus. So what are we saying here? So Rutherford told us that the electrons essentially just orbit the nucleus however they wish. Okay, and the nucleus is positive and the electrons are negative. But what Bohr is saying is, well, since we know that's not exactly true, what might be true is that maybe the electrons can only exist at certain energy levels. So remember we said things like n is equal to 1 or n is equal to 2. Okay, those are our energy levels. And we're going to talk about why it's called n and all those things in just a few moments. That's where we're heading. Okay, but for now, understand that since we see those quantized line spectrum, or line spectra for each individual atom, okay, there must be some other explanation. And so Bohr is saying that there must be discrete energy levels that house the electrons, and they're not just randomly scattered around the atom. Okay, so we use the symbol n for these energy levels, and this is called the quantum number. And it has to be a whole integer, so it's like 1, 2, 3, 4. Okay, so what's good about the Bohr model? Well, it explained the line spectrum of elements and compounds, and it acknowledged the energy, absorption, and emission as discrete packets of energy, and therefore we could calculate E is equal to h nu. The not so good about it, the theory is successful only for the element hydrogen. So Bohr introduced the quantum idea artificially, but never fully explained it theoretically. And just sort of to reiterate what we're talking about with the n levels. Okay, so you see n is equal to 1 closest to the nucleus, and then up to n equals 5, and it goes beyond this, but for illustration, you don't usually draw an infinite number. Obviously, that's impossible. Okay, but what he's saying is we have in discrete energy levels, n equal 1, n equal 2, n equal 3, and that's what will then cause these individual lines. And I sort of explained this already. Whereas we excite from any of the energy levels, so from say 1 up to 5 here. Okay, and then if we have a complete relaxation from 5 to 1, that's going to give us a certain energy. If we have relaxation from 4 to 1, that will give us a certain energy, or 3 to 1, or 3 to 2. These are going back to 2. Okay, so if we have those relaxations, it will give us these discrete lines. So in other words, each one of these relaxation has a different energy associated with it. So it takes a different energy to excite to a certain level, but it also gives a different energy off when it relaxes to a certain level. So that's what would cause these individual lines to appear. Okay, so maybe what's a better theory? So if the Bohr model isn't complete, what's a more complete model? Well, we can use mathematics and probabilities, and this was done by Schrödinger. So he applied the idea that electrons behaving as a wave to the problem of electrons and atoms. So he developed the wave equation, otherwise known as Schrödinger equation. Okay, I'm not going to ask you to write the Schrödinger equation or solve the Schrödinger equation. If you go on to take quantum somewhere else, that will probably be the time that you do that. But it has a general formula. So h times psi is equal to epsilon pi times psi. Okay? And you don't have to necessarily know what all of those mean right now, but just understand that the Schrödinger equation, or the wave function, is known as psi. Okay, so it's this sort of U with a line in the middle. And what this does, so I'm interested for you to know what this equation does more than knowing the actual equation itself. Okay, so what this does is it describes an area in which the electron can be found in relation to the nucleus. What it doesn't do is denote the exact location of the electron, but only the probability of knowing the location of the electron. In other words, it sort of gives you a general area. So it tells you the general shape and probability of where the electron might be. It doesn't tell you it will be exactly there. It just says, well, it'll be in this general area. And when psi is solved, 4 solution values result. And these values are referred to as the quantum numbers. So n, l, m sub l, and m sub s. And we're going to break down what each one of those means and what are the accepted values for it. So just know the wave function describes the area in which the electron can be found, of course in relation to the nucleus, but it does not denote the exact location. You get 4 solutions from the Schrödinger equation. They give you n, l, m sub l, and m sub s. Okay, so kind of explaining a little bit more about Schrödinger equation. Okay, so what quantum mechanics tells us about an atom's electrons is the wave nature, not the particulate characteristics, of the electron that explains the chemical and physical properties of matter. In other words, we have to look at the wave properties rather than the more like matter type properties, okay, to start to explain some of these physical phenomenon. Okay, so the electron is no longer viewed as a small piece of matter orbiting around a nucleus, but a cloud of probability. And where do we get that cloud of probability? Okay, we get this from the Schrödinger equation, of course. Okay, and lastly, we have Heisenberg's uncertainty principle. Okay, and this is one that's sort of often misunderstood, and I will do my best to give you the real answer to what is this Heisenberg uncertainty principle. Okay, so the first thing, why the wave duality nature of the electron makes it difficult to know the electron's exact position and the velocity at which it's traveling or orbiting around the nucleus. Okay. So why is that? Why does it make it so difficult? Well, this is where Schrödinger principle comes in. So if the position of the electron is known with exactness, then only the probability of the electron's velocity is known. If the velocity of the electron is known with certainty, the position is only probable. So what is this telling you? Okay, this is telling you that you can either know the position or the probability with exactness, but you can't tell both at the same time. Okay, and why is this? Why would this be? And this is sometimes said as like, oh, the observer is changing the outcome. That's not really what he's saying. Okay, that's sort of it's a misinterpretation of it that sort of makes people feel good, but isn't true. Okay, so what he's saying is, if I physically manipulate an atom or a set of atoms in such a way that I know the position of the electron, okay, then I no longer know its velocity. Or if I want to know its velocity, well, I've knocked it out of orbit now, so I don't know its position anymore. Okay, why is that? Well, it's because you have to physically interact with the electrons. So if we have an electron, so we have just an electron in orbit, and say we want to know its position, or say we want to know its velocity, so we take some photon or some electron beam, let's just say a photon for now. Okay, so some h nu, and we knock it out of position because we know exactly how to fire that photon in the exact position. Well, now we've kicked the orbit, or screwed up the orbit. Basically, we've kicked the electron out of its orbit. So now we may know where it is, but now we no longer know how fast it is. Or we may know, maybe we're experimenting with how fast it's going, but now we no longer know where it is. Okay, so that's the uncertainty principle. So you can know one or the other, but you just can't know both at the same time. Okay. So we can say that electron's energy can be defined with exactness, but its exact position relative to the nucleus is known with limited certainty. So we generally know the energy based on Schrödinger equation, okay, but knowing its exact position more than just a cloud of probability is a bit of a problem. Okay, so what does that give us? This gives us the probability density function. Okay, so this is the total probability of finding the electron in a particular point in space. And this is in 3D space, keep in mind. So what does this do? So what it does is it gives us the shape of what we call the orbital. And the orbital is based on this cloud of probability. So where are we likely to find the electron in relative vicinity to the nucleus? Okay, and these all have a different shape. And this last little bit here, all we will really do is A, we'll look at those quantum numbers, and B, we'll look at the actual orbital shapes. Okay, so the first one here is called the 1s orbital. So n is equal to 1. And then what type of orbital is it? It's the s orbital. So it's at energy level 1, and it has S shape. Okay, so what you see is all these blue dots give you the probability of finding the electron in this area. So notice there's none out in this region. Okay, they're all pretty close to the nucleus, and you can sort of see, hopefully, that there's sort of a sphere shape to this. I know it's hard to draw, really. It's hard to see, really, with just a flat slide like this. But what they're trying to tell you is that at some distance r, so some radius from the nucleus, and in all 3D space, so in all directions, x, y, and z, okay, this is the highest probability of finding this electron within the atom. So you're not going to find it way out here. If you look there, you won't find it. But it could be somewhere, or should be, somewhere inside of this blue cloud. Okay, and that's based on solving Schrödinger equation. And if you were to put that mathematically, so in other words, if you were to take psi squared for this, you would most likely find, so this is telling you the most likelihood of finding the electron at distance r. And what you see is the further and further we get away, so the further to the right we go, the further we get away from the nucleus, the lower probability we have, and going down to basically 0. And the closer we are to the nucleus, the higher and higher our probability goes, essentially going to infinity. Okay, so if we want to find the electron in the s orbital, we have to look close by the nucleus, and it's in this sort of sphere shape. Okay, so what do these quantum numbers tell us? We said, okay, well, this equation gives us the quantum numbers. What do they actually tell us? So they tell us the location of the electron in relationship with an atom's nucleus, and they're essentially like the address of the electron. So they specify the area of an electron occupies, or the area an electron occupies in relation to the nucleus, so kind of what I've been saying. And each quantum number describes an allowed energy state of an electron. So notice this term, allowed. Okay, what we'll look at is that there's only certain values of each quantum number that are allowed. Okay, and we're going to talk about a few principles here. So the first one is the Pauli exclusion principle. Pauli tells us that no two electrons can have the same set of quantum numbers. So therefore, every electron surrounding an atom's nucleus has its own set of quantum numbers, and each orbital can only have two electrons, and they have to have opposite spins. So if I have two electrons in one orbital, they have to have opposite spins. So that's Pauli exclusion principle. It tells us no two electrons can have the same set of quantum numbers. When I was in high school, so you talk about Pauli exclusion principle, okay, and we talk about Hund's rule, we talk about a few things like this. And I remember my teacher saying that these are all Russian scientists. He always told us that we better obey Pauli, because if not, he would come beat us up. Okay, so obey the Pauli principle. Okay, so let's look at each individual quantum number and see what values are possible for it. Okay, so the first one, as I said, is N, the principal quantum number. This indicates the energy level the electron occupies. And these have to be whole number integers. So they have to be like 1, 2, 3, 4, 5, etc. Okay, it's just whole number integers. Okay, this is also known as the shell. So it's the energy level, or the N level, or the shell. Okay, so that's N. And that will always be a whole number integer. Next one, L, is the angular quantum number, which indicates the orbital shape. So is it an s orbital? Is it a p orbital? Is it a d orbital? Well, that's governed by L. Okay, and values of L are determined by up to n is equal to n minus 1. Okay, so L is up to n minus 1. Okay, so if n is equal to 1, the only possible value, so if n is equal to 1, the only possible value of L is 0. Okay, why? Because 1 minus 1 is 0, so the maximum value of L is 0. Oops, sorry. Okay, if n is equal to 2, notice I can have two values of L. So n minus 1 could be 1, so it can be as high as 1. So it can still be equal to 0, but now it can also be equal to 1. Okay, so 0 is S, 1 is P, 3 is D, etc. Okay, this is known as the subshell. So this is the shell, or energy level, and then S, P, D, F, these are all your subshells. Okay, and so n can be any whole number integer. L can only be up to n minus 1. So it can still be lower numbers, but that's the highest number it can be. Okay, so if we have L equal to 0, this is our S subshell. L is equal to 1, this is our P subshell. L is equal to 2, this is our D subshell. And if L is equal to 3, this is our F subshell. We won't look any higher than that. Okay, the next one, M sub L. So we have N, we have L, now we have M sub L. Okay, so this is the orientation quantum number. So it indicates the area the electron occupies. So values of M sub L are determined by plus or minus the value of L. So it explains why there's only one type of s orbital, 3 types of p orbitals, 5 types of d orbitals, 7 types of f orbitals. Okay, so in other words, what they're saying there is if L is equal to 0, well, M sub L can only be plus or minus 0, which we know doesn't really make sense. But anyway, there's only one value possible for M sub L, so that's why there's only one s orbital. But for instance, in the p orbital, okay, I have L is equal to 1, so now the value of m sub l can be minus 1, 0, or positive 1. So I have three orbitals inside of the p subshell. Okay, so next thing, m sub s, this is the magnetic quantum number. This indicates the spin of the electron in the orbital. So this just tells us, is it positive 1/2 or negative 1/2? In other words, is it spin up or is it spin down, which is an easier way to talk about it, I think. But make sure you understand that it's either plus 1/2 or minus 1/2. And those are the only values possible. So it has to be spin up or spin down. There's no in between. Okay. So here we have n is equal to 2. So what could our values of L be? Well, n equal to 2, so it could be up to n, or up to 1. So we have 0 and we have 1. Okay, then remember, m sub L can be up to plus or minus L. Or we have that many, we have plus or minus L number of suborbitals or orbitals. Okay, so if for the instance of the p orbital, m sub L can be equal to minus 1, 0, or 1. So you end up getting 1, 2, 3. And then each one of those can hold 2 electrons. And once they are filled with 2 electrons, they have to have opposite spins. So remember, they can't have the same address. So if you're putting them into the same orbital, they have to have different spins. Okay, so let's look at a couple shells here. So n is equal to 1. So remember that L is equal to the maximum of n minus 1. Okay, so if we were to solve this, obviously this is not difficult, but if n is equal to 1, L is equal to 1 minus 1 would be 0. Okay, so the only possible value of L here is just 0. And then m sub L can only be up to plus or minus 0, which really is just 0. Okay, so we only have one orbital there. Okay, same thing for n is equal to 2. Only now we have two possible solutions. So now L, again, is equal to n minus 1, which is now 2 minus 1. So it can be a maximum of 1. So that means you can have a value of either 0 or 1. Okay, so that's why we get now the introduction of the p subshell. Okay, within the p shell, m sub L can be equal to minus 1, 0, and plus 1. Okay, so that's why you get those three orbitals. And remember, each one can hold a upspin and downspin electrons, so 2 electrons in each. So a total of 6. Okay, lastly, when we get up to n is equal to 3, now L is equal to n minus 1 still. So 3 minus 1, so that's equal to 2. Okay, so now we get the introduction of the d orbitals. And m sub L, again, can be a maximum of, so now we say m sub L can be minus 2, minus 1, 0, plus 1, plus 2. So you get 1, 2, 3, 4, 5, and each can hold 2 electrons for a total of 10. Okay, so you just sort of build in this way as you go. So as you go higher in energy level, now these different shells open up based on the allowed principal quantum numbers. Okay, so make sure you can write a set of quantum numbers. So if I was to say, write a set of quantum numbers for an electron in the d orbital, okay, make sure you could write that all the way out. And it could be any of the 5 or any of the 10, but make sure you can write at least one set, or make sure you can identify a set that's good from a set that's bad. Okay, so I'm almost done here. We just have 1 or 2 more concepts, very basic, and then we'll do a couple example problems and we'll be done. Okay, and we'll look at some more orbital shapes right at the end. So this next thing, so we have this n sub L, or m sub s, I'm sorry, the spin. Okay, so how does this relate to magnetism? I think this is kind of an interesting, kind of cool thing to talk about. Okay, so one thing can either be diamagnetic, meaning a substance that is not attracted to a magnetic field, and this is because you have paired electron spins. So we have spin up and spin down in all of our orbitals. But if something is paramagnetic, it is attracted to a magnetic field, and this is because it has unpaired electrons, like this. So maybe in 2 different orbitals, we have 2 spin up electrons that haven't been paired. So this would be attracted to a magnet, whereas this would not. Okay, so this would be para, this would be dia. So dia like die, just remember it that way. Dia like dead or die. Okay, so if they're spin paired, no attraction to a magnetic field. If they're not spin paired, then it's attracted to a magnetic field. And that would look something like this. So you don't have to know this, okay, but just kind of understand this concept. So this is the example of oxygen, or just an example in general. Okay, so this is an example of singlet and triplet diradicals. Okay, so if we have singlet spin, okay, this is spin paired. So the HOMO is the highest occupied molecular orbital, LUMO is the lowest unoccupied. So here the LUMO is empty, the HOMO is full. Okay, but notice we have spin paired electrons here. So this would be diamagnetic. This middle one is unstable and we really don't see it that often. Okay, but the one on the right, this is our triplet, and we call it triplet because there's 3 possible positions of these electrons. And we call this the SOMO, so singly occupied molecular orbital. Okay, so this one on the right, this is an example of a magnetic atom or magnetic molecule. Okay, so this is actually an example of something like O2. So oxygen can have either singlet or triplet spin states. Okay, and that's one reason why if we have liquid oxygen, it's actually magnetic. Okay, so this is what we call the molecular orbital diagram, and you don't have to know how to draw these for this class, but just to show you, in its highest orbitals, we have unpaired electrons. So here we have two oxygen atoms coming together to form O2, and we combine their orbitals and we put in their electrons. And one possible configuration for this is that we have this triplet state, where we have these unpaired electrons. So if you pour liquid oxygen into a very strong magnet, see this stuff in the middle? It actually floats within the magnet because, and now evaporates very quickly, but because it is spin unpaired, because it's paramagnetic, you get this magnetic effect. Okay, so just make sure you can identify a magnetic atom versus a non-magnetic atom. Okay, so now we're just going to do a couple of these problems. I think it's 1 or 2. And then we'll move on and we'll look at a couple more energy, or a couple more orbital shapes, and then we'll be done. Okay, so which of the following sets of quantum numbers is not allowed? So this is the type of question I could ask you. So this will be N, L, M sub L, M sub S. And there will always be presented in that order. Okay, sorry, that's terrible handwriting, but they'll always be in that order. So N, L, M sub L, M sub S. They'll never be in a different order than that. Okay, so give this one a try. See if you can figure out which one of these quantum numbers is not allowed, or sets of quantum numbers not allowed. Okay, so let's look at this. So first we have N is equal to 4. Okay, no problem there. It's not like 3.5 or 1.5, something like that. No, it's 4. So that's acceptable. Okay, L. So L can be up to N minus 1, so it could be up to 3, so 2 is not a problem. Okay, M sub L could be up to plus or minus, what do we say? So this is up to 3. This is 2. Okay, so if we could go plus or minus 3. So minus 1 is perfectly fine. Then we have spin 1/2. Okay, so this one's good. Okay, 8, no problem. Okay, 4, so that's less than 8. That's no big deal. Okay, 0 is definitely possible. Okay, then minus 1/2, that's possible. Okay, so the next one. So our N level is 2. So that means L can be up to up to 1. Okay, no problem there. Now our M sub L can be equal to, so remember M sub L, for if our L is 1, can be equal to minus 1, 0, or 1. So here we have an M sub L of 2. So this is no good because of that 2. Because it's N sub L, that M sub L value is not allowed. If we look at the next one, N is equal to 3, L can be up to 2, that's fine. M sub L could be up to plus or minus 2, no problem there. And then spin of 1/2, no problem. Okay, so it's number 3, and the reason being is because of that M sub L value. Okay, and there, that's the full explanation. So if N equal to 2, Okay, you can have a L number of 1 or 0. So L is equal to n minus 1. So if L is equal to 1, then n sub L can only be minus 1, 0, and positive 1. Okay, so that's your explanation. So this one is not possible because of this too. Okay, so now I want you to list a set of quantum numbers that would represent an electron in a 3p orbital. Okay, so give this a try. See if you can write a set of quantum numbers for that. Okay, so hopefully you were able to come up with a set of quantum numbers. I'm going to give you all of them. So n is equal to 3. So I can have, in other words, I'm on the third energy level. So for P, the L number will be equal to 1. Remember, 0 is S, 1 is P. So that means my L has to be equal to 1. So that means my M sub L values can be minus 1, 0, or 1. Okay, so M sub S has to be either plus 1/2 or minus 1/2. That's just spin up or spin down. Okay, so that means my possible answers for this are all of these. Okay, so 3, 1, minus 1, positive 1/2, and then the same set with an opposite spin. Okay, and then you just go on down for each value of M sub L. Okay, so minus 1, 0, and 1, and then 1/2, 1/2, minus 1/2, minus 1/2. Okay, so any of those answers would be correct. So it just says list a set of quantum numbers. So any of those answers could be correct. Okay, so this last little set here, we'll talk about the basic shapes of s, p, and d orbitals. And I'll show you a set of f orbitals because they're kind of weird. Okay, so remember if L is equal to 0, then we're in the s orbital. Okay, the s orbital has the lowest energy within the principal energy level. And the probability of plot of the s orbital is spherical and is shaped around the xyz axis plot. So the s orbital, in other words, looks like a sphere centered around the nucleus. Okay, in other words, centered around the origin. So remember, it's in 3D space, so you have z, x, and y. Okay, and it'll just sort of be a ball. And as you move up in n level, so as you go from n is equal to 1 to n equal to 2, you still have the same shape. It just becomes sort of like a nesting doll situation where there's sort of, or if you ever had one of those really big jawbreakers that has different colors as you go through it, it's sort of like that. Okay, so they're just sort of nested within each other. Okay, so something like this. Okay, so as you move away from the nucleus, okay, so if you go from n is equal to 1, n equal to 2, okay, you start to sort of just get this like nesting shell idea. Okay, where it's still spherical, but they're sort of stacked on each other. So it becomes less likely to be found extremely close to the nucleus, but as you take one step away, so a little bit further, now it's even more probable. Okay, so what you end up with is, like I said, these sort of concentric rings. So you have your inner, and then the next one, and then an even bigger one. Okay, and it just keeps going on and on like this. Okay, whereas that's the most likely place to find that electron in that energy level. It's still spherical in shape, but now it becomes more like a hollow kind of sphere. Okay, so just think about them as being like concentric, sort of stacked spheres, if you can imagine that. Okay, they all have basically the same shape. They just start to become a little bit hollow as you go out. Okay, so I would expect you to understand what an s orbital is and how it's shaped. Okay, next one is our p orbitals. So we first see these where n is equal to 2. Okay, this is our second lowest energy level. And we call the p orbitals, we say they have a dumbbell shape or a bow tie shape. And we have 3 p orbitals, remember, since we have minus 1, 0, and positive 1. Okay, so we have 3 p orbitals, and they're the px, py, and pz. Okay, so just they lie along the axes of just a basic 3D plot. Okay, and so they have this sort of shape like this. Okay, so if I was to ask you, for instance, to draw a set of p orbitals, you want to make sure you draw the x, the y, and the z. So the best thing to do is to put them exactly like I have them here. Okay, so 3 different orientations, or you can show them on the same. You can keep, in other words, you could draw this 3 times and change your axes, but make sure you change them correctly. But I think the best thing to do is to draw 3 sets, and then just draw the p orbital on the right axis. But notice they all have this p shape. So this would be the px. Why is it the px? Because it's the p orbital on the x-axis. This is the py. So same shape, okay, but on the y-axis. So this would be the py because it's on the y-axis. And lastly, we have pz, okay, because it's on the z-axis. Okay, so hopefully that makes sense. Just know that if you have this basic set of like bow tie or dumbbell, and they're lying on the axis, this is your p orbitals, they're px, py, and pz. Okay, then we step into the d orbitals. Okay, so now we have L is equal to 2. Okay, so there's 4 d orbitals. So it makes a note here that we start to get these in the 3rd subshell, but the d orbitals are actually in the 4th period. We'll get there when we start talking about periodic trends. We don't need to know that for now. Okay, but there's 4 d orbitals, dxy, dxz, dyz, and then dx squared minus y squared. And these have like a cloverleaf type shape, aside from dx squared minus y squared. That one's, well, no, it has the same shape, but it's a little bit different. Okay, and then the last one we have dz squared. And I'll show you exactly what these look like. Okay, so this is our set of d orbitals. Okay, so notice this time we're not on the axis, except for, where is it? This last one, dx squared minus y squared. That's why I said that one's a little bit weird. So notice that these are between the axes. So they're like in the planes. So that's how they get their name. So dxy or dyz, why is it the dyz? Because it lies in the yz plane. Okay, so this would be the z and the y. So that plane. So it's like if you imagine this, it's so think about these as sort of being in a sheet of paper. Okay, so all in one plane. They're all in that zy plane. And then dxy, why? Because they're in the xy plane, and then dxz because they're in the dxz plane. And then this next one, so dx squared minus y squared, so it's on the x and y plane, but it's actually on the axis now. So now we're in this plane, okay, but now we're actually on the axis. And then lastly, dz squared. So you sort of have this same dumbbell shape, but now you have a donut around it. And it is a hollow donut. It's not a solid donut. Okay. So I wouldn't necessarily ask you to recreate these. What I would expect you to know is that if A, what is their principal quantum numbers, but B, if I was to show you a set of orbitals like this, could you tell me which ones they were? Okay, and the last one is the f orbitals. Okay, and there's 7 types of these, and these are kind of crazy looking. Okay, so this is not something that your average chemist would necessarily even be able to draw you. Okay, but I wanted to show them to you because they look kind of weird. Okay, so I wouldn't expect you to really know a whole lot about these. I certainly wouldn't expect you to draw them. If I was to show them to you, since they are so wacky looking, I think I could expect you to know that these are the f orbitals. But beyond that, I wouldn't ask you a whole lot. Okay, so that is the end of the quantum mechanics chapter. So that will wrap things up for today.